Okay, and we have also, as explained previously, streamlined or blunt body. Okay, so what are the forces? We mentioned that bodies interact with the fluid, and then they have forces acting on the body itself. So let's take a look on this example of having the airfoil, the one that we used as an example previously. As you can see over here, as the fluid moves relatively to the body or the other way around, you're going to have pressures. Just like what we have previously, you have pressure on all the surface with different magnitude and directions over here. So as you can see over here, the pressures at the bottom is highest at the front, but as you can see at the top of the airfoil, you actually have a negative pressure compared to the bottom one. So that's what creates lift actually. Other than that, there's actually also a friction force. So this one acting on normal to the velocity, and this one actually on the velocity, it's in the same directions, and it is due to the friction between the fluid layer and the wall of the object. So you have shear stress that causes the frictions, and the resultants of those two forces, the pressure force and the friction force, will create lift or drag depending on which one is greater. So we will base our analysis on those two forces that acting in the body. Okay, the frictions. So the shear stress or shear wall stress, tau W, is caused by the viscous effect. Remember, at the wall you have no slip condition, but on the free stream you have like velocity. So there's a relative movement over there. So you're going to have a stress, and the highest will be on at the wall. And the other force is the normal stress due to the pressures. And then, although it sounds simple just to determine what's the normal press or the pressure stress and the shear stress, it's actually really difficult to determine each of it. So what we measure usually is the resultant of those two forces, whether we're going to have a lift or a drag, and its direction, we only have the resultant. So the forces itself, if we analyze this component of the body at the surface of the body with the area of dA, the friction force or the shear force will depend on the tau W and the area, while the pressure force will depend on the pressure and the area over here. So on the x direction, you will have dfx equal to pdA cosinus theta as the angle between this and the reference, plus twdA sinus theta over here. So this is the x component of this forces acting on this elemental area. And the x and also so this will create the drag. That's what makes the trying to hold the body, trying to drag the body motions. So if we have the elemental force, if we want to calculate the total force, the drag force, we integrate them along the x. So we have these equations. On the other hand, there is also on the y direction force, you have dfy, which is minus pdA sinus theta plus twdA cosinus theta. And this y component creates lift, which is also a force. And if we integrate, this we will have these equations. So that's basically what we the principle of the forces that acting on the bodies. Any question until this point?
No, sir.
Okay, good. So let's continue. Let's assume we have two plates with different orientations. First is having a horizontal orientation like this. Second has these orientations, vertical. And then both immersed in air fluid that is moving at the velocity of u, okay, and the pressure P and the shear stress, wall shear stress distribution is given by this. So the question is, what is the lift and the drag on each of the plate? Okay, so but this basically is the same. We need to find what's the drag and what's the lift of each of the body. Okay, so we need to calculate first let's say the lift. Okay, the lift is caused by the pressures at the top and pressure at the bottom. But since the area the same between the top and the bottom, also the pressure is the same. P equal to Px equal to 0, it means it's gauge pressure. So the lift will be 0. Since we have same velocity on top and at the bottom also same pressures, then we have 0 lift. Okay, what about that lift is the vertical direction force. What about the one that in the flow directions on the horizontal one away in our case? So that's the drag. Drag is equal to the summations of the
shear force on the top
force,
and the
yeah,
bottom.
exactly. So we have this TWDA plus bottom TWDA. If they are the same, since the material are the same, surface rollers are the same, area are the same, so we're going to have 2 of TWDA. For our case, it is given TW distribution as a function of x is equal to 1.24 times 10 to the power of minus 3 divided by square root of x. So this is a theoretical shear stress distributions. Assume that is known. If it is known, then we just need to substitute into these equations. So we substitute this into this equation, it will become 2 times and integrate along the x value, 4 feet, 0 to 4 feet, 1.24 times 10 to the power minus 3 divided by square root x, and dA is the area. So the area will be the area of this is given, oh yeah, this is the width is 10, yeah. So the area will be 10 times the dx itself. So this is if I make it three-dimensional. So this is 10, the width into that direction. And times dx, dx is the length of it. Times, so this is dA. And this is TW. So we're able to get the drag 0.092 pound. We ignore the the thickness on this. Okay, so that's we have there is about 0.1 pound. So what would be the force acting when you have this kind of shape? Vertical one. First, we need to find the lift. But since we can assume that this is so small, the area, as you know, the lift is TW times dA. If the dA is equal to 0, then lift is equal to 0. So remember, it's also we can also assume because of the same lift between the front and the back, and we have this one 0. What about the drag? So the drag here now between the one on the front and the one on the back over here. PDA minus PDA, also integrate PDA. And then it's also given the pressure distributions. It is given by the problem. So we just substitute the pressure distribution into our equations from -2 to 2 feet. If we take this is as y equal to 0, then you have -2, and you have 2 over here. So if we include that, we have 55.6 pounds as our drag. So you can see here, we have this same area actually over here, but because of the orientation, we have almost 500 times drag because of different orientations. Previously, we have 0.1 drag over here, and then on other case, we have 55.6. So that's the principle of calculating the lift and the drag of flow over immersed body. But what's is simplified in our example here. On the real application, it is very difficult to determine this, to know what is the TW distribution along the length over here. So this one is, for our example, is given, which is hardly apply if we do it on a real life. Also, the pressure distributions on this case, we know the pressure distribution. Although this is easier than to know the shear stress distributions. For example, if you have like certain shape, and then you want to know what's the pressure distributions on this one, then you may be able to know it by putting like as many pressure sensor in your surface, but it's not really applicable because, as you see, a slight change on the geometry will change the pressure. So the pressure distributions is hardly known. So that's the simplification that we made for our case over here. Okay, any question until this point? Okay, let's continue then. And without that detailed informations on the shear stress and pressure distribution, like we mentioned before, TW and P distributions, then the drag and the lift are difficult to obtain by integrations. Even if we know them, sometimes it involves integrations of complex functions. And then to simplify that, to have it more applicable, we introduce actually a coefficient because it's easy to measure the force directly than to measure the pressure or the shear stress distribution. We just measure the force. For example, if we put a load over here, then that will represent the lift. So we know the lift, and then we also have what we call the characteristic pressures. So we introduce the lift coefficient defined as the lift force divided by the characteristic pressures, or the drag coefficient as the drag force divided by same the characteristic pressure over here, rho u squared times the area. So this is an effort to simplify the measurements and the calculation afterward. So we find CL through experiments. Okay. So for a given shape object, the parameters that are important, I think we have mentioned that earlier, is the size, the orientation, the speed, and the fluid properties. And if we use the non-dimensional parameter to represent all of this, it is represented by the Reynolds number, because Reynolds number involves the size, the speed, and the fluid properties. The Mach number represents the speed. And for the flow with the free surface, Froude number. Okay, the free surface, what is free surface? Free surface means you have interface between two fluid instead of one fluid. So for example, between water and air, a motion that involves these two interface, then you have a Froude number. But for now on, let's focus on the only body and one fluid. So you have a Reynolds number, and the Mach number will be important on this one. So just anyone have any idea what's the Reynolds number represent?
The whether it's laminar or not kan?
Yeah, it's determined the characteristic of the flow. But what's it represent of? What parameter represented by Reynolds number?
Density times speed times the length divided by viscosity.
Yeah, those are the parameter represents. Okay, but actually in physical term, the Reynolds number is the ratio between the inertial force and the viscous force. So there is a viscous effect on it. So there is a inertial force. Okay, I'm gonna have a different. So density related to the inertia, the mass that it has, and you have velocity over here, and you have characteristic length. Remember, this is also important when you analyze the internal flow. You use D. You use D, the diameter of the pipe, or the hydraulic diameter of the conduit, for example. But in external flow, you use what we call the characteristic length. Usually, if it is flow over pipe, then the length of over plate. So the length of the plate will be your characteristic length. If it is a cylinder, for example, then the perimeter will be your characteristic length. So it's different from the internal flow, the Reynolds number definitions. But still, it represents the inertia and the viscous force ratio. It represents the size, the speed, and the fluid properties. While the Mach number is ratio between the speed of sound, sorry, the speed and the speed of sound. So it represents the speed itself. So in our discussion later on, these two will be important, especially the Reynolds number. When you have small Mach number, then the Reynolds number is important. Okay, so lift and drag vary as a function of Reynolds number. So and we're talking about laminar and turbulent flow. If you remember, the pipe has a transition of 2300 from turbulent to laminar. But for this case, it's actually pretty big. The transition occurs when the Reynolds number is 5 times 10 to the power of 5. So you have laminar flow and you have turbulent flow. So we can actually analyze or discuss the characteristics of flow past an object based on the Reynolds number. Okay, for most external flow, when the characteristic length around this one and then the velocity around this one, the resulting Reynolds number is from 10 to 10 to the power of 9. For Reynolds number greater than 100, means like it's until 10 to the power of 9, for example, the flow are dominated by the inertial effects. For Reynolds number less than 1, the flows are dominated by the viscous effect. Remember, so Reynolds number is the inertia divided by viscous. So you greater Reynolds number, greater inertia. Smaller Reynolds number, bigger viscous. Okay. Let's consider a flow above a flat plate as the simple one. Try to have start from the simple one. So we have three figures over here. The top one is when you have small Reynolds number. It means you have a viscous effect dominance on it. And you will see the streamline of the fluid, water or air, is easily deflected by the presence of the plate. Okay, so this happens when the Reynolds number is much uh, very small, 0.1 and less than 1, for example. So the viscous effect will be bigger and wider. For the Reynolds number of 10, in this case, for example, viscosity is not really important, so that you have the viscous effect region is smaller. What is U less than 0.99 U? It means like the velocity at this region is less than the free stream velocity. So you have free stream velocity over here. So it means the velocity in this region is smaller than the free stream velocity. And even at the higher Reynolds number, the regions become much, much smaller until you have this very high Reynolds number, 10 to the power of 7. Then you can see that the viscous effect is becoming very small, only near the vicinity of the wall of the plate itself. On the other regions, the inertial force is dominant on this one.
Pak,
Yeah, go ahead.
so for this condition, when we have a lower Reynolds, a higher Reynolds number, there's less likely to be drag force ya, in this condition ya, in this orientation maksudnya.
Yeah, so drag. Well, we have to be careful on this one. The drag is not only caused by the friction. Okay, so for this case, you're right. For this case, the low Reynolds number, or actually for most of the case, the low Reynolds number represent bigger drag. But if you have the one that is not captured by the Reynolds number is the shape or the geometry. So it means like if you have this shape compared to, for example, this shape, then you have two components of drag. First is the shear stress at the wall, and the second one, you're still going to have the shear stress. The second one is the pressure force, also cause drag. Remember, so the drag and the lift are combination of the pressure force and the shear stress force. So for example, in this case, if you have this shape, small plate on this in the direction of the flow, then you're right. The bigger the Reynolds number, the less the shear stress or the drag for this shape, because you have a negligible pressure force because of this. Okay, but if imagine that you have change your shape into like this, then you have a small shear stress, because actually the flow will be separated over here, so you will have small fluid layer attached to this shape. But remember, you have the pressure force, which will cause the drag also. Okay, so just to a little bit visit on this one. So the lift and the drag is a function of two component. Oh, this one is not representative. Let me go back a little bit. This one, yeah, this one. So you see here is combination of the pressure and shear stress. The lift also combination of the pressure and shear stress. So you have to consider, for our case on the plate, flat plate like this, the P can be considered the same because P over here and P over here on the top are the same. So they cancel each other. But the TW become big. But you're going to have a different like this one because you have P force over here and this one is small. So the point is we have to be careful because not only Reynolds number affecting the lift and the drag. Remember the size, the orientations, the speed and the fluid properties are affecting it. Reynolds number is only capture the length, which is the size, the speed, and the fluid properties, but it doesn't capture the orientations. Okay, I hope that's clarified. But for specific case like this, then the less Reynolds number, the bigger the frictions, right? The bigger the frictions over here, the bigger the viscous effect over here. With the highest Reynolds number on our case, the flow is dominated by inertial effect and the viscous effect are negligible everywhere except in the region very close to the plate and in the relatively thin wake region behind the plate. So over here. So the viscous effect only important on very small area nearby the plate and also the wake regions over here. Then you have to consider the viscous effect. On the other regions, all of them are inertial force. So this is an example of wake regions. Okay, since the fluid must stick to the solid surface, no slip conditions, there's a thin boundary layer region of thickness delta. So we actually introduced a new term over here, boundary layer thickness. I believe you have learned that when you analyze the boundary layer concepts, which is much, much smaller than the length, okay, in which the fluid velocity changes from U to 0 on the plate, no slip conditions. And the thickness of boundary layer increase in the direction of flow. So like in our case, we have this. So this is delta. And delta is increasing along the x direction. Okay, the flow within the boundary layer can be laminar or turbulent, depending on the parameter involved. And the streamline of the flow outside the boundary layer can be considered no effect of the viscous. So it won't bend, it's just going to ignoring the presence of the plate. So it's nearly parallel to the plate. Also, yeah, ahead, above, and below the plate is negligible effect of that. Well, kita punya lagu siang nggak? Okay, any questions?
No, sir.
Okay.
No, sir.
Okay. Now, another case when we have the flow over, before we have a flow over a flat plate, now we have a flow of cylinder over here. Excuse me for a minute. So we also going to analyze based on the Reynolds number. As you can see over here, we have 0.1 Reynolds number, very small Reynolds number. And then actually almost similar. For a very small Reynolds number, you have a big viscous effect. Very important throughout it bends a lot the streamline of the flow. Okay. The second one, when you have Reynolds number equal to 50 in our case. So the region of the cylinder with the viscous effect are becoming important. See the difference over here. So because of the viscous effect is important, it's kind of like pull the streamline into the cylinder itself, and it's essentially symmetric in front and the behind of the cylinder. But when you have a high Reynolds number, now you have a separation. So over here, you kind of like having the streamline attached still to the wall of the cylinder. As the higher number, as the Reynolds number increase, you have the separations. So you have separations at the back. So you're going to have a different different flow characteristic in front and behind the cylinder, and those different will create uh, drag because of the different, for example, different velocity and different pressure. Then it will cause drag over here. The flow spread from the body at its dispersion point. Dispersion point can vary. For example, in our case, you have at this point, you have the fluid streamline separate from the wall. It's because at the high Reynolds number, the inertia is important. So because of that flow, the inertia will cause the streamline to separate. It cannot follow the curve path around to the rear of the body. As it goes higher, the Reynolds number, then you have the separations even become earlier. Then you have wake region that is much bigger, and you will have you're going to see a different flow characteristic in front and behind that will cause also or influence also the drag. Okay. Okay, and then spare. So those are for cylinder, and this is for spare. I have a video that you can the flow over a spare. Okay, here you go. So it's starting with low Reynolds number, and then you're going to have a high Reynolds number. So you see this at this point over here, you still have attachment. until this point, and if the Reynolds number increase, for example, increasing velocity, you will see the aspirations moving earlier from this point to the front of of the the sphere, and you have the wake regions increasing on the back of it. So if we analyze each of the conditions for the Reynolds number small, the flow is wholly laminar and then symmetrical. It still can the viscosity is still big because it's still attached to the wall. There is no form drag. Oh yeah, previously we can actually identify different drag, the friction drag and the form drag. The friction drag is due to the friction, the form drag is due to the pressures. Okay, if you have a higher Reynolds number, the flows separate, and then you have eddies or turbulence going on the wake regions, but it's still on the relatively short wake regions. Increasing the Reynolds number will increase the wake regions, and then the separation also become earlier. And then if you have even higher Reynolds number, then you have a very early separation and then high turbulence on the wake regions. Okay. So we able to analyze for some geometry, and we able to appreciate the difference of the flow characteristic across or over a flat plate, cylinder, and sphere. Any question at this point?
Oh, Pak.
No, sir.
Okay, yeah, because we now going to into a boundary layer concept, which require a little bit mathematical tools to solve for. But it's important to get to use this concept to solve the flow over immersed body. So consider a plate over here. We have a plate with the length of L on the x directions. And we have a fluid, air or water going over it, or of course below it also. Due to the viscous effect, in the beginning, you will see that the uniform velocity of wave change. So you will have a zero velocity at the wall, and then you go into the full velocity, free stream velocity at the far away from the wall. There is a certain boundary that you still have this velocity distributions. Above that boundary, you can assume that they are going to be the same, the velocity at the free stream velocity. And there is the boundary layer. And then mathematically point of view, it is defined as a layer where you have the velocity less than 99% of free stream velocity. So as long as your velocity less than 0.99 u, then you have a boundary layer over there. So it's delta. So this is also called the boundary layer thickness. And the boundary layer thickness changes as the flow directions increase. So you have the laminar boundary layer where the behave as a laminar flow, and you have a turbulent boundary layer. Because if you remember, the Reynolds number is defined as, you can also use U L divided by the viscosity over here. L is the length. So as the length increase, as the Reynolds number increase, and then you're going to go through a transition between laminar to turbulent boundary layer based on the L value on this one. Okay. How do we describe the flow over here? So this is also going to give you, if we try to find the all velocity distribution, remember to find lift and drag, we're going to need the shear stress and the pressure distribution, and the shear stress distribution can be obtained from the velocity distribution, du dy. Yeah, it's mu du dy is the shear stress. Shear what do you call it? Shear stress, yeah, TW over here. But it's difficult to represent this whole point as one equations. So the boundary layer concept is important because it's actually divide the velocity distribution at the boundary layer, and you can assume the free stream velocity at the above it. So we scrutinize, get into detail into this boundary layer, which is actually fairly small in the term of couple of millimeter, for example. So it's really small, but it's really important, the boundary layer, to get the friction and the drag, the lift and the drag also on this one. Okay, so before Prandtl, so one of the breakthrough of the fluid mechanics is when Prandtl introduced the boundary layer concept over here. So before Prandtl, we ignore the viscous effect. So if we go back to the Euler equation is actually a simplification of Navier-Stokes equation. So bear with me. Let's take a revisit to the Navier-Stokes equation. Navier-Stokes equation is actually a momentum equation that has three components. First, due to the pressure gradient, okay. Second, due to the body force, for example, most common is the gravitational, because of the height difference and so on. There is also another term is called diffusion term. This is because of the viscosity, viscous effect. The Euler equations, or you can simplify later on the Bernoulli equations, ignore this. So they don't have this term. Remember Bernoulli equations, delta P, and you have the velocity change due to the change in the velocity. They don't have the viscosity component over there. And then that proved to be contradict with the experimental observation. So we cannot ignore the viscous effect. So so that's why for the Euler equations, only two components over here, rho g and then grad pressure. So this and this, they are the same. So yeah. It should be an equal signs over here. Okay. So the Euler equations have limitations. They have different results on contradict many experimental observations because there's things that there is no boundary layer, so you just go with the free stream velocity, but that's not true. So there is important, although thin boundary layer that going to influence the flow. So that's why we cannot ignore this. And then the Prandtl approach to incorporate this viscous effect, this diffusion term, is by using the boundary layer concept. So that's why it's become a breakthrough on the fluid mechanics in 1900. So, and it still applies until now. So in 1904, Prandtl introduced the boundary layer concept, which based on this premise. First, you have to divide it into two regions, the boundary layer and the free stream. One close to the solid boundaries and the other covering the rest of the flow. And then only in the thin region adjacent to solid boundary or the boundary layer, the effect of viscosity is important. For the rest of the flow, the inertia is important, so you can ignore the viscosity. Okay, and even you can consider them as an inviscid, means like viscosity 0. So it allows the solution of viscous flow problem that would have been impossible through application of Navier-Stokes to complete flow fields. So that's actually what the breakthrough is. We divide into two different flow fields and solve for the boundary layer using the viscous effect and the free stream using the inertia one. Okay. Inside the boundary layer, the friction is significant, and across of width of which the velocity increases rapidly from 0 is no slip conditions at the wall to the value that inviscid flow theory predicts, like the Bernoulli or the Euler one. Outside the boundary layer, velocity gradient normal to the flow are relatively small, so it's like straight line, and then you have come to the boundary layer, you have this. Okay, the viscosity is not 0, but it can be considered in viscous, like this again. Okay. Some definition on this one, on the boundary layer of the solid surface. It can be divided into laminar, transition, and turbulent. And for a finite length of the plate, L, yeah, Reynolds number defined as U times L divided by viscosity over here, P. For the infinitely long flat plate, we use X. So the Reynolds number become Reynolds number at X, point X, Ux divided by viscosity. Okay. Now boundary layer has a thickness, right? But we can divide the thickness term into three boundary layer thickness. First is conventional boundary layer thickness. As we define, it is the distance from the wall where the velocity becomes 0.99 u. That's the boundary layer thickness. We have a displacement thickness. It's actually the same displacement where you're going to have. So you see it over here, you have the region over here, and if you set them into a rectangle over here, the head will be the displacement thickness. You have the same amount of displaced fluid layer as the displacement thickness over here. So here, I think this is represented over equal displacement, equal areas over here. That's displacement thickness, or delta star. The third one is the momentum thickness. Where is it? Momentum. It's not yet momentum yet. Okay, for the boundary layer thickness, already defined. For the displacement thickness, yeah, the distance of the plate that will be moved so that the loss of mass flux due to the reduction in uniform flow area is equivalent to the loss of boundary layer forces. So mathematically, it's defined as this. Delta star is equal to integration 0 to infinite 1 minus the velocity at that y divided by the free stream velocity dy. That's the definition of boundary layer displacement thickness. And the momentum thickness, boundary layer momentum thickness, is the distance the plate will be moved so that the loss of momentum flux is equivalent to the loss of the boundary layer actually causes. So it's symbolized as theta. U over U times 1 minus U over capital U dy from 0 to infinite. Okay. To better appreciate the boundary layer thickness concept, let's go into an example of air flowing inside a duct, 2 feet square duct. And then we need to determine what is the velocity of the air or function as a function of x. So you can see that at the what's the velocity over here, because it will have a different velocity between this point and this point. Note here that although this is, you can see this is flow inside the dot, but the diameter of the dot is considerably higher than the boundary layer. So it can still be considered as a free stream in the middle over here. So the boundary layer influence is very thin compared to its diameter. Some of you may question why we didn't consider this boundary layer concept during when we analyzing the flow in a pipe, for example. Actually, we did. Although it's not done analytically, but we actually incorporate the boundary layer effect into the friction loss or the major loss, HL. Those are include those friction loss over here. And we did that from the experiments because we have the body diagrams, all of them from experiment. We have the surface roughness effect and so on. All of them are from experiments. And those actually incorporate these frictions. Any question until this point before we move forward to solve this example?
Pak, jadi this pipe flow can be considered external flow as long as the diameter is larger than apa ya, Pak?
Then the boundary layer. And the boundary layer thickness. So delta is much smaller than the diameter. So and also you have sufficiently long enough, yeah, so that the boundary layer can develop freely. For example, if you have small diameter in our case, like for example only this part, only until this point, for example, then you will see that the boundary layer will not develop into fully, and then you will merge the boundary layer from the top and then from the bottom. But if you have enough length, sorry, enough diameter and also enough length, then we will have we can consider them as an external flow. Does that answer the question?
Yes, Pak.
Okay. Let's continue. Over here, oh, it's good. Given the we have given the boundary displacement thickness, which is actually in a real case really difficult to get. But for this example, just to appreciate how the boundary layer going to affect the fluidity distributions, let's assume that we have that given or known from the experiment, for example. Okay. Okay. This first we need to consider them incompressible force so that we can uh, ignore the change on the density and so on. Then also the continuing the equations apply also. So Q1 equal to Q2. So the debit also the same. Although the area will decrease, right? Because you see that over here, the area due to the boundary layer, the area will change. So in the beginning, the Q is equal to U1 times A1. So you have 10 feet as the velocity, and the area is 2 feet square. So you have 40 feet square over here. And that is the maximum, because you have the maximum velocity over here. And that actually equal to the integral of UdA. Okay, and if we take a look on the displacement thickness definitions, we go back again. This one, displacement thickness 0 to infinite 1 minus u over u dy, and this is defined over here previously. The flow rate across section 2, which is this, you're going to have a different cross section over here. Let's call it U2 over here. And then, so if you have 40 feet cube per second equal to UdA, is equal to U times 2 feet as the maximum side over here, minus 2 of displacement thickness and square, because this is a square dot. So this comes actually from this figure. So you have a 2 delta star over here. So the area become, this distance will become 2 feet minus 2 delta. 2 delta star. And you have to square it because it's a square. So this is the area. The area become that. So that's why we have this area over here. U times 2 feet minus 2 delta star square is equal to the 40 feet square, because you still have the same debit, same continuity equations. And we know the delta star equations. We substitute the delta star equation into our equation over here. This is delta star, 2 times delta star. 2 you take, so we here 2 times delta. So what if it's square equal to 4u1 minus 0.007 x to the power of half square. And if you take the u out, you're going to have u as a function of x. That's what we're looking for. It means the velocity will change as the x move. So velocity change over here. Question, is it faster or smaller velocity than the incoming velocity?
Faster.
It's faster because you have less area. You have the continuity equation u1 times a1 equal to u2 times a2. Since a2 is smaller than a1 because of the displacement thickness, then u2 will increase. So that's why u1 is equal to 10 and u2 is equal to increasing according to x. Become faster as the thickness of the boundary layer displacement increase also. Okay. Any questions?
No, sir.
No, I think okay, I will okay, that's an example. The next question will be how to solve boundary layer. Well, it is already solved by Blasius. So it's actually a student of Randall. So we have the solution already. We solve actually for a flat plate how the boundary layer thickness, displacement thickness, and the momentum thickness can be obtained. We use two approaches: Blasius solution and momentum integral equations. First, we do with the Blasius equations, which is limited only to laminar boundary layer, and for flat plate without a pressure gradient. Means like only the friction that caused the drag. There is no form drag. There is no form caused by the pressure distributions, but just friction caused by drag caused by the friction caused by the shear stress. Okay. Assumption for the Blasius equations. It is expected the component of velocity normal to the plate is much smaller. So you only have the velocity on the direction of the flow. This one. There is no vertical velocity. So yeah, usually can u and then this is v, velocity on this direction, but we ignore this. And then the velocity distribution, of course, we're going to have u variation along the x directions, but again, we ignore that. Only the u variation along the y direction. So this is the assumptions. And zero pressure gradient. And then the viscous force is comparable to the inertial force. I think we can stop until this point. So we okay. Just one little approach over here. So this is the Blasius solution. The derivations is pretty length if you want to go see on the textbook, but on the basis of this assumption, the Blasius come up with these solutions. What's the solution for the boundary layer? Well, we want to know what's the pressure, what's the velocity distribution in the boundary layer. and then the blasts give that. This is the distribution. How about the thickness of the boundary? This is the thickness of the boundary layer. It's given by this. So if you know the Reynolds number, which is a function of the x and velocity and the viscosity, we have to determine the boundary layer thickness, also the boundary layer displacement thickness, and also boundary layer momentum thickness. So those value give you the solution for the boundary layer equations. So the solution of the boundary layer equations actually mainly you want to get what's this? What's the velocity distribution of this? And what are the thickness of the boundary layer? Okay, I think we can stop over here. We can, or maybe one more, a little bit, one more. This one. So this, as you can see, this is the solution is. This is the velocity distributions. That's what we're looking for. If we know the velocity distribution, we will see that it relates to the shear stress. If we know the velocity distributions, we can find the shear stress, tau. And then from tau, we can get the frictions and finally the drag. Like that. Okay, I think that's all for today. So any questions? No?
Oh, Pak.
Okay, a quick recap, okay? We have discussed the characteristic of the flow, the force that is acting on the body immersed in the fluid flow, which consider the lift and the drag. And then we also visit the boundary layer concept, and until we reach the Blasius solution. Although we didn't discuss the derivation of the Blasius solutions, but we have given you the solution of the Blasius for the boundary layer equations. Okay, so I think that's all. Remember, you have homework due tomorrow, yeah, 22nd, I believe so. And then this one we will continue to discuss on the next meeting, and I'll post this on the Immersed so you can take a look on this one. If you confusion, just ask on the group. I'll try to answer that. So thank you very much. If you don't have any question, I'm going to end the class.
Yes, sir.
Thank you, sir.
Thank
Yes,
you
sir.
very much. Have a
Thank you,
good
sir.
Terima kasih, Pak.